still talking about the topic of natural language processing, but of course that it's not just about natural language. We have covered in the beginning from text, and we have also started to use idea of how to process word and semantics. And last week we have talked about, say, suppose you have a large language model, but the large language model's knowledge may not be specific enough for us to be answering questions from a specific domain. Then we can try to collect some domain-specific information and use them, use those documents. Those documents could be text, could be PDF, could even be pictures, could be video, and collect them and train our own vector database. And once we have a vector database, which is domain specific, then whenever a user asks a question about that particular domain, then we'll go to the vector database to try to find information that will be related to the query, to the question. Okay, then we can use that from the vector database, the information related to that specific query, then include them as part of the prompt to ask LLM and to ask LLM to generate answers. Okay, so so basically the overview, we have covered this 2 or 3 weeks ago. Basically the whole kind of the technology foundation of the natural language processing, starting from word representation. When we have a whole bunch of sentence, okay, or a whole bunch of from some literature or from some library, then the first thing we need to do is try to find a way to represent the words, okay? And then we have talked about, say, rather than just encoding, we want to be able to capture some meaning about each of those words. Okay, so therefore we convert them into tokens, and then we try to convert them into some vectors. The vectors will be in some multi-dimensional space. Okay, and those vectors for each of the token or each of the words will have its own position. Okay, and in the position of each word in the in the vector space, somehow will give us some hint about some semantics. Okay, and we have say for example here originally you have a word which is apple. It could be encoded in some specific numbers in the vector space, but when we try to understand the meaning of an apple, okay, then we can try to relate the apple with other things in their relative positions in the vector space. So here it shows that for each country, they could be in some vector space, but they're related, the relative positions for their capitals will be in some vector space with a similar direction and similar distance, okay? And so we have talked about several things that is it can be used to build such vectors, okay? Now, today I want to talk about a few foundation technology for us to be building the natural language processing. And so I have already shared this slide, which is going to be talking about transformers, but specifically what I would like to do is for us to together, let us watch this video, which I have I enjoyed the video very much because that the video allow us to visualize when we're talking about all this vector, what does it mean? Okay, I am sure many of you have seen this, right? Have you? Do you know about this? The videos produced by this group, the three blue and one brown. Have you seen it? How many of you have seen video from them? Okay, this is a video which is they have actually produced a lot of videos related to the deep learning and also computer science and such, and data science. I try to. Okay, but this one specifically, this is one of the course. They said this is a course about deep learning. Okay, and this was published 1 year ago, and this is chapter 6. Okay, and so if you want to watch the whole thing, you can go to the link in this particular course. Let me see where. I think from here. Okay, you can see that they have shown the some information about the course. Okay, so you can try to. So let's watch together video. Okay, I will stop it. I will then we'll continue. Hold on a second. I need to.
Here's the important context I want you to have in mind.
Okay.
As a quick recap, here's the important context I want you to have in mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words.
Okay, so we have said that when you have a sentence, actually supposedly that it is supposed to break them into tokens, and so most of the tokens will be subwords. But in the discussion in this video here, they simply say, actually, let's use the whole word. Okay, so you compare this is the token, but this actually are using the whole word as the unit for the discussion.
The first step in a transformer is to associate each token with a high dimensional vector. We call its embedding. Now, the most important idea I want you to have in mind is how directions in this high dimensional space of all possible embeddings can correspond with semantic meaning.
Okay, so I like to use the video because that it can show that each of the word or each of the token of the word, okay, actually it would have some specific position in the hyperspace, and this will be represented as vectors, okay? And so you can see that, when we start to put them into this hyperspace, sometimes it looks like it's randomly positioned in some place, okay? But actually, those positions, actually later in the video, you will show that actually they have some specific meanings.
In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much, much richer contextual meaning. I should say it.
Okay, so let's listen to this carefully again, this particular sentence, because it captures the idea of the
Embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is...
Okay, so the transformer, the usage of the transformer is that actually you have one original word, king, which originally in the vector space is in here. Okay, but the meaning of this one here originally is just a general king. But it is trying, when we are using transformer or some kind of processing, we are actually trying to change the position of this word king. It is still K-I-N-G, but we're going to try to move it around in the vector space so that this king is going to be capturing some of the information from the sentence. Okay, so you can see that in this short, kind of a video here is trying to show you that original position is king. Okay, but whenever you take some information into the knowledge of this king, it's actually changing its original position from here. Say, for example, after it knows that he lives in Scotland, then this king actually will move from here to the space around in here, live inside. Okay, so originally the king's position is here, and this is going to be the place that for all people who live in Scotland. Okay, so this is actually, that means that the people who are living in Scotland, and if somehow from the sentence, we know that this particular king in the sentence is supposed to mean this king is living in Scotland, then the king actually will be moved to be close to other information, which is in the vector space, to be also meaning that they live in Scotland.
Progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning.
Okay, so if we later find out more and more about this king from the other sentences in the text, then originally we only know that this king actually lived in Scotland. Then we also can find out, say, okay, actually the king actually murdered predecessor. There will be a whole group of people or some facts related to murder to the group of the predecessor. Then also it has the relationship to say that it is relating to people or to the area who are in Shakespearean language. Okay, the people who speak that traditional English language. Okay, so originally we have a vector space which is in here, but by taking all of this and you'll be moving all that vector space position eventually to be in some place, and that particular place is no longer just one word, but actually that particular place is already capturing all those information in that specific vector space. Okay, that's what the transformer is trying to do.
I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing. So don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American true mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these based on the context.
Okay, so here again that we have one word, that mole, okay, but depending on other words, okay, around in that mole or in that particular sentence, we know that from the semantics, this mole here refer to some animal, this mole here related to some size, and this mole here related to human face, okay? And so the idea of the attention is to say, when I see the mole, how can I ask all the words around me and to let me know that, okay, are you referring to the mole, which is going to be in the whole area, which is referring to the animal? Or are you referring to something which is, for example, carbon dioxide can give us a hint. This mole here is not about animals, but it's about certain, kind of measurements, okay? And this mole here, actually, because we have the words like biopsy, which is around close to this mole. So therefore, we know that this mole here is not about anymore, it's not about the size, but it's about some medical. Okay, so using the information form around that particular word, we want to be able to adjust the vector space in the vector of the mole in the vector space from one position to another, to another, to another. Eventually, its position in the whole vector space will capture everything related to the information surrounding that particular word.
The one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference.
So initially, when we have just entered, the sentence, the mode vector values, okay, they will be the same in all three sentences, okay? And then you can see that, okay, all of this information will then be used, and the modes, the values in the vector for this mode will be changed.
To the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things.
Okay, so taking every word in front of it or around it, okay, we are changing the original position of the tower in the vector space and move them somehow in a new position, capturing that information, and then also capture, if you have another information, then you will move to some other position. Okay, so you can imagine originally this tower here, okay, is going to be about some generic information about anything about tower. But when we put the Eiffel in there, then it has a meaning of Paris or France in that region. So you move the tower, okay, that word or that particular word's vector space into this area. Okay, this is about France. Okay, then when we see the word miniature, then the miniature would tell us that it actually is not talking about France. Okay, it's actually talking about that specific Eiffel Tower, but now because of miniature, so therefore it's moved to totally to a different area, which is about some toy or some token or some souvenir. Okay, so if we have a way to go into the vector space, if you look around this area, then you'll find this vector is about miniature Eiffel Tower. But somewhere close to here, you might find another one which may be miniature, not Eiffel Tower, but Empire State Building, which is in New York. Okay, you may be able to find something if I say, like look around here, a little bit closer, you may be able to find miniature 101 building. Okay, so each area in the vector space actually will already capture some meaning, but miniature Eiffel Tower probably will be around those miniature French souvenirs. But miniature 101 building probably will be somewhere close to here, but yet another close area, which is about souvenirs from Taiwan. Okay, but originally tower itself has its very simple vector definition, which is from the word to vector. Okay, which doesn't carry any semantic information except to say I am a tower. But once you to put this Eiffel in front of the tower, once you put this miniature in front of the tower, the representation of that particular vector has been changed from here to there. So I think we can probably stop here and we can start to go into our lecture today. Okay, so so today we want to spend a little bit more time to talk about the attention. Okay, the meaning of the attention is exactly what the video has just shown. The attention is for us to try to change the definition of the vector, okay, for each word by using the information surrounding the original text, okay? So the problem with static attention, like I said, that, okay, they are static. Every time we see the word it, started originally it will be a generic it. It doesn't have any specific meaning. It just means it is something to be referring to something else. But what is it referring to? Well, without looking at anything surrounding that particular word, that particular token, nobody knows. Okay. So attention, try to say, I'm going to try to use some contextual embedding, okay, some contextual thing into that particular words embedded, okay, so that each word will have a different vector expressing different things depending on the surrounding. Okay, so originally I have some very specific value, but once I put the attention, when I see some other word, then that value of that vector will be changed. The value will be changed again and again. Okay, and that is when we started to use all different type of all different type of things in there. Okay, so suppose we have a sentence: the chicken didn't cross the road because it. Okay, so now suppose you have already seen the sentence up to here so far. When you see this it, if I'm speaking to you, what do you think this it is talking about? This it here, is it related to because? Yes and no, because this it here, actually, when we say because, then you would know that, okay, I need to look information in front of me. Okay, so this it here says that I need to see around here. And this it here then is going to try to find some words in front of me that is referring to an object, because it is a representation of object. And so all these words here in this sentence would need to let this one here know to say what my object is. THE doesn't refer to an object. Didn't doesn't refer to an object. Cross could be an object. Why do I say cross could be an object? What is a word? If I use cross as a noun, what will be cross? This, right? So cross itself could be an object, but of course it could also be a verb. Okay, but we don't know yet. Okay, so here you can see I have the chicken in object, cross could be an object, road could be an object. Okay, so therefore this it here will try to decide that whether this it here from the three, okay, and all three here need to tell it to say, I'm in front of you and I'm an object. So when you have this sentence here, it could be referring to me. It could be referring to road. It could be referring to cross. It could be referring to chicken. Okay, depending on the sentence. Now, if we look at this sentence, the chicken didn't cross the road because it was too tired. So from the tired, it means that it must be something which can move around. Otherwise, if it's just a static object, you wouldn't be able to say, I'm too tired. So from this tired, then we can cross it to say, okay, could it be the road? Could it be the cross? Or could it be chicken? Okay, so from our common sense now, you can say, because the tired appears in the sentence, so therefore this it here must be not talking about the row, because the row never get tired. Okay, cross. Cross doesn't really get tired. Or you can say cross could be tired because if we use cross to be a verb, when I try to cross something, okay, it could be tired. Or if I say cross is actually a noun, then you couldn't get tired. Okay, so if I'm just trying to say it, okay, so this it here, if I use this cross to be a noun, then it couldn't be tired. So therefore, out of all of this, the only thing we can say is that the chicken could be the only thing that referring to this type. Okay, so by looking around one sentence or the text or the whole article around you, when we have one specific word, originally it has an embedding in some particular vector, it will be affected. We can try to move it around using all the words around it to see that how it can change the position of that, so that this it here eventually will find a specific location in the vector space that is referring to say, oh, this it here is talking about chicken. Okay, then from then on, this it and this chicken will be used equivalently, okay, in the rest of the sentence. Okay, so the idea of the attention is trying to say to build up the contextual embedding from a word by selectively integrating the information from all its neighboring. That's what I just written. I have an it here, but I need to look at all the things, around me. It could be a chicken, it could be a roll, okay, and then this and that. By integrating all this information, then I will be changing the vector, okay, that particular vector in the original location into a null space. Therefore, it says that the word is to attend to some neighboring words more than others. Okay, that's the idea of the attention. So attention here is to say, you have probably seen this picture before. When I have a sentence and they have many, many words, and each of the words, when I have it here, it needs to ask all its surrounding word to say that, okay, I need some information. Who can tell me that you are an object? Then all of this will refer to say, okay, I'm an object. And later, if somehow it can find out to say, okay, there is a word tired also in there, then you can cross out to say the roll couldn't be tired. So therefore, this roll is not, but the chicken is. Okay. And what is going to happen is that once it has identified this it to be very related to the chicken, okay, then this it, original, this vector is pointing to here, which is the generic man, it will be actually moved to be in the vector space, which is very, very close, if not the same as the position in here. Okay, so attention is be looking for everything around you, okay, which is trying to help the particular vector to change its position. So it's actually the attention mechanism is a mechanism. It's actually the method that we have created in the deep learning here to help compute the embedding for a token, selectively attending to and integrating information from all the surrounding tokens. In other words, it's a method to really just to try to change the vector, change my vector's value from all other vectors around me, and put all of their vector values in me. Okay, because we're talking about mathematically, we are actually changing, moving the vector position is just like changing the vector value. And changing the vector values when we're doing the attention is trying to add other people's vector value into me. Okay, that's the whole idea of the attention. Okay, so the idea of the attention is to say here originally I have some vector space values. Okay, then I'm going to ask other people. Okay, I'm going to ask other people and use their information to change my values. Say, for example, X bar here is original my value. Then I'm going to ask other people to say, okay, do you have something? Do you have something? Do you have something? Do you have something? Is your information related to what I am trying to talk about? Okay, If I'm here is a it, then I'll ask who actually would be a noun. If this is chicken, then I say, okay, I need you. If this said I'm a road, then I need you. Okay, and I will put all this information into here to help me change my value, taking your value, and add it to become to be a new value. I'm moving my position from the original value, and I take some of your value, take some of your value. So therefore, I'll be moved around in the attention space. Okay. So mathematically, it's simply to say that, okay, I have a whole bunch of x1, x2, x3, each of the words before, and now I want to be able to predict what's going to be the next word. Okay. And the next word is going to be somehow by taking all the scores from all other words related to me, and then I simply add it up. When I add it up, then I'll produce one value, which is going to be everything in front of me, but I'm not taking all of you in the same way. I need to have some way to decide how much I'm going to take from you. Okay, if you are not a noun, I'm not going to be worried about it. If you are a noun, then I'll take. If you're chicken, okay, then I'll say, okay, chicken could be useful to me. Here you say this is roll, this could be useful to me. Okay, but if you this is this is two, this is something, okay, those are not useful to me, then I'm not going to take your value. So those scores is going to be in this alpha here. Okay, so the alpha here will try to decide to say how much of you should be useful to me. Okay, and I'm going to try to consider all the words and try to decide which words among you is most important to me. But I'm not taking everybody equally. I'm going to be trying to decide which one actually has the largest value. Okay, and I'm just going to put that value, and then I'm going to add it into me. X1 will put something in me, X2 will put something in me, X3 will put something in me. So if this is about chicken and this is it, then you will say, okay, yeah, chicken is very important to me. So the tension really is just to try to add all the other values, okay, the weighted sum from all previous work into me, okay, so that I will be able to try to decide what is my information. So here, suppose I have an it, this is xi, then you can see that each of this actually is a vector. Okay, I will be taking each of the vector, okay, and then I'm going to try to decide how much of that vector value should be in me, okay, and that will change the meaning of the it, okay. So the detailed design of the transformer is to try to compute how do I decide, okay, I'm a word, what is the word in front of me? What are the words in front of me and what are their meaning? Are they important? Are they useful? Or are they something that I need to know? And use all of that, okay, in order for me to decide how much of that should be put in my vector, okay? So you create these three mechanisms. One is a query, is to say, I am now, I'm it. I am now, I am, like say the tau. Okay, so your current position, your current element said, I am something. And then you ask a question, okay, I'm sorry. Your current question, your current element here, you ask a question, say, I'm a tau. Okay, is there anything in front of me that would change my meaning of a tau? If you have THE, it doesn't change. If you have something, doesn't change. But if you say that, okay, I'm a 101 building, okay, I'm building, then if I ask anybody has anything that is referred to some particular region or particular location, if you see there's a word in front of me, it says 101, okay, then I want to catch it because 101 will tell me I'm in Taiwan. If I have another word in front of me says this iPhone, then yes, again, I want to ask. So I will be asking around everybody to say anything. Okay, I'm the tower. Please tell me whether you have some information to tell me in some location. Okay, you might have a query which would ask to say that, okay, I want to know how big I am. I'm just a tower. If any of you, okay, is related to the size, it's a huge tower, it's a high tower, it is miniature tower. All those, okay, should tell me you are there. Okay, so this is the idea of the query. When we try to run this attention, each word will come up with a query to say that, please let me know if you have such qualities. You have a size quality, you have a location quality, you may have a color quality. Okay, you have something. So each of the query here will be asking all words in front of me to say, can you tell me anything that you fit? So if you think about this query here, and if you compare this when we discuss about computer vision, we will have a picture. We will try to do the convolution. What is the meaning of a convolution? We have a picture, right? We run through the convolution layer, we run another convolution layer. Each of the convolution layer is also asking some question. What's the question convolution layer trying to ask? Features. Each convolution, you would have some filter design, right? You would have some kernel, right? And that kernel actually will say, okay, can you tell me this picture here? Do you fit in this picture? Can you tell me that I can find an ear of a cat? Can I find an eye of a cat? Can I find the fur of an animal? So query in the machine learning is something that you have original data, and then you have some operation. You say, I want to ask some specific information about me. I want to know what's going on. Okay, so I'm going to come up with a question. Here we use the query to ask that anything meaningful, size, color, location. Okay, it could be this and that. It could be warm, it could be cold. And we have many different dimensions. So you can have a query here to be asking all things like this. In the computer vision, we use the convolutions. We have many different layers. Each of layer has many different filters, many different kernels. Each of the kernel actually will be asking specific question. Inside of the picture, is there some particular feature that I can identify? If I can identify that, then the output will be 1 or will be greater. Okay, if it doesn't have anything, we use ReLU to say it doesn't have that information. Okay, so in the computer vision, they also have the query by this convolution. In here, we are using the query matrix here to be asking questions about all these different dimensions. Key is going to be something, okay, everybody is going to be trying to come up with the response to your question. So if you say, I'm it, okay, and can anybody tell me that you are a noun? Then the key here will be deciding to say, oh, yeah, actually, I am a noun. Okay, I am a chicken, or I am a roll. Okay, so this key here will answer to the query to say, yes, I match what you are asking. So once I have the query and everybody else compare with their property, okay, and they find a match, then they will be coming to say, okay, I match what you are asking for, so therefore my value should be useful to you. So my value should be used to change your position in the vector space and move it in some other, okay? And that is going to be the weighted sum, that is going to be the value which is going to be added into your original value, okay? So you can think of to say that here I have a query, okay, and the query here will be trying to ask to say, I am it, okay, can anybody tell me that you are a noun? Okay, can everybody, if you are a noun, can you tell me something more about yourself? Then this, okay, original, they all have their values, okay, their original values. But we will ask the query, then the query, okay, will be matching with the key, okay, and with the key and the query, if there's a match, then the key would decide to say how much of the value in here should be used to update the vector space in here. Okay, that would be the idea of the transformation. Okay, so basically that we're trying to ask the machine to learn this will be a query operation, that will be key operation, and then will produce the value which is to be added into the original space. Okay, and the whole thing here is just mathematics. Eventually, you're going to do the all this query will be multiplied into this the weights that we're going to be the machine to be the machine learning algorithm will be learning, and the key here also will have this, and then will have its own weights, and then the value will have its own weights. Okay, so you perform the operation, you decide the score, and then you decide to do how much of each of this individual word, okay, should be added into the current positions. Okay, so here you can also see that. Suppose that we have x1, x2, x3 in the whole sentence, then x3 here will be asking the question. Okay, will be asking the question from x1 and x2. Okay, and the x1, x2 somehow would tell it to say that, okay, whether I'm related or not. And when it knows that whether it's related or not, then the value of them will be used, okay, in here, okay, and therefore the value will then be to put it together to update the original value by taking some value from here and taking some value from here. How much is going to be taken from each of this is going to be computed by our machine learning algorithms, which is similar to like our I'm sorry, this is natural language, but it's very similar to our computer vision. Whenever we have a convolution, the convolution, when we take the original picture, each of the convolution will tell us how much values they have produced, okay, and they will be added into the new input, okay. So we can come back to look at the video, okay, and see that whether we can find something in here. Okay, let's just try to continue to watch the video.
Meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how, after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word "was," will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns.
So here you can see in this sentence here, we have two nouns. One is forest and the other one is creature, okay? But the creature is just general embedded. You know, anything, it could be a creature, but we are going to try to change the original embedding of the creature by using the information from blue, by using the information from fluffy. So by taking the fluffy and blue, their values, and add it into the creature's vector space is not going to be, its position in the vector space is not going to be in its original location, but you'll be changed to some other location. And that particular location will already have the idea is a fluffy, meaning that it's, you know, puffy, you know, it's not flat, and blue, okay? And so therefore, even though it is still the vector for the creature, but already you'll be capturing the information about fluffy, about blue. The same thing about forest, okay? The forest here, originally could be just general forest, but by taking verdant, okay, that word, then we will be changing the vector of forest from the original position in the vector space into some new location.
What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. they also encode the position of the word. There's a lot more to say about the specific.
Okay, so in the actual when we are doing this in the transformer, each word in the sentence is positioned. The first word, the second word, the third word, the fourth word, that position information also is encoded in its original vector. Okay, so the position thing doesn't really change what we have just said, but the actual original vector already have the original meaning of that particular thing and also the position in the whole sentence.
Way the positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, hey, are there any adjectives sitting in front of me? And for
Okay, so that's what the machine learning is trying to do. The first thing it does is that I know that I'm a creature. So now I'm going to ask the question, which is a query, to ask anybody in the sentence here to say, okay, are you in front of me? Because you're in position. So you know that whether you're in front of me or not. Secondly, adjectives. Okay, anything which can be used to describe something about creature, let me know. Okay, so we'll be asking this question, but we're going to format this into a query, which is going to be something that is going to be sent to every.
The words fluffy and blue to each be able to answer, yeah, I'm an adjective.
So this query will be matched with their current value because their current value should already have some information to say they are actually an adjective, okay? And they are describing, say, for example, blue would have the value to say, I am actually encoding the information, I'm a blue color. Okay, and this one here would actually have the information to say, I am actually the fluffy, kind of surface. So by asking the question, and if they somehow would match this request to say, I am an adjective, then the system would take some of your value, and put your value in my vector. And so therefore my vector's value will be changed from the original creature into fluffy blue creature, which is going to be one specific location in the vector space. Okay, and from then on, when I try to learn something, I use that modified vector that would capture all the information about the semantics of the specific thing that I am talking about in this particular sentence.
And I'm in that position. That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q, and then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token.
So when we try to process a sentence, every single word will come up with a query, and that query is supposed to be asking every other word in the sentence to say that, can you give me some information about something? Okay, this word here to say that I need to have some adjectives. So anybody who is describing your color, your shape, or something, let me know. Okay, so this is the query is going to be asking that. This blue itself, okay, when you see the blue, original, it is referring to some particular vector in the vector space. What kind of question do you think you could be asking? I'm a blue. What should I ask? Anybody in front of me, what should they ask? The single word blue. If you are blue, if you want to ask anybody else to say, how can you change me? What would be asking? Is there anything here that somehow hinted you are a paper? Is there any of the word in front of me saying that you are a creature? Is there anything in front of me even say about music? Because blue could be a color, it could be about music. Okay, so you could be asked, you should ask a question to say, oh, I'm a blue, but can somebody tell me what you are and you are in this sentence? And if you can tell me that, okay, there is something describing something related to a paper or something related to a house, maybe I start a sentence, the house is blue. Then I know that this blue is not just general blue, but it's a blue for a house. Okay, so it could be asking that is anybody in front of me is a noun. But I'm a noun, so I'm asking is anybody who is an adjective. So everybody is going to be asking questions about something related to their meaning. Okay, and we will train a weighted metrics here. Okay, and this one here will convert everybody's value into their specific question they want to ask about their neighbors. Okay, that will be the first step. Everybody would come up with a query. After that,
from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it's some.
Okay, so basically, the transformer, this is the first step. Okay, when you have some sentence or some text, okay, and we give it to the system will compute its original vector, okay, and then you will be using this trend wave to try to come up with the query, and then also we try to come up with the some meaning, okay, and they will match, and then original or eventually they will be used to update that. Let's take a break and we'll come back to talk more and see more about this video. Okay. To bring the whole thing into the large language model. Okay, so the motivation for us to have this discussion is that suppose that you have a sentence in your input, okay, which is a whole sentence like this, and it's referring to one specific word. Okay, now it is talking about it. So we need to know that this it here, what is referred to, okay, because it is a very generic word. And by using the mechanism to have the it to be able to ask questions to all its surroundings to say, I am it. Okay, I need to know more information about myself. So therefore, can any of you tell me what I am? And so the query you'll be asking probably is, for example, we have said that, is there any adjective in front of it? Okay, and any adjective or, no, I'm sorry, in this particular sentence, is any name, any noun in front of me, okay? And so the query will be sent to everybody. And everybody else in the sentence, originally it has its own value, x1, x2, x3, x4. So these values, x1 and x2, each of these, the vector has some knowledge about itself. So it should be able to say, I am a noun, okay? And I am actually something which is related to chicken, okay? Or some animal and this and that. And this one here can also say that I'm a noun and I'm referring to something which is about transportation, about in the world and this and that, okay? So the query which is going to be asked could be a very generic one to say, anybody, you are a noun, let me know. Then the query, okay, with all of this, okay, will then be converted, the information will be converted into a key. And the key will match with the query. So if the key somehow have some information the query is asking for, so the query says, any of you is a noun, and then chicken here said, yes, I'm a noun, okay? Then the chicken's key here will match with the query, and then these two multiply with a positive value or with a non-zero value, then you would take the value from the original x2, and this value here then will be added into the query. So the query now, originally it is in some vector space. It will now to move to some location that would have some meaning about that particular thing. Here is a
to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns.
Okay, so just like I said, if you are a noun and you are asked a question, you could be asking that everybody said, anybody is an adjective. But if you are an adjective yourself, you're a blue, then you could actually be asking other people to say, any of you is a noun. Okay, so it's kind of a query for everybody to be generated in their queue. Actually, it's going to be reverse of each other. But when they ask a query, but their own key somehow would be able to match the other. If somebody asks me for adjective and I'm an adjective, I will respond to say, yes, I'm an adjective. So therefore, my value should be given to you. But if you are an adjective, you're asking for a noun and I'm a noun, then I'll say, oh, I'm a noun, and my value will be given to you. So you'll be combining the information from all different words into each other. Okay, and so eventually that everybody, going through all this different transformation, you will have captured more information about yourself because you are in that particular context. Okay.
At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries.
Okay, so here I'm asking the question, and here everybody will go through this transformation to produce their key, and their key actually, you can think of that to be a vector to capture the key information, the most important information about myself. When somebody asks a question and you actually have that information, then the two will match. When the two match, okay, then you know that your value should be given to this value to change the vector so that it's now going to be having the right information in your particular vector.
This key matrix is also full of tunable parameters. And just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other.
So the query will be in some specific, vector kind of asking for some directions, and this one here would, have some direction information. And if the query and the key match, okay, I'm asking for a noun and you are a noun, then you will match. Then the match will be multiple. When you have the dot matrix of that, you will have a positive value. When you have a positive value or have some strong value, that means the value in that particular word should be given to this particular vector. Okay? And that will be changing the vector value set.
In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key query pair. I like to visualize a grid full of a bunch of dots where the big.
So after you multiply this query and the key matrix together, the value which is produced is going to be, some of them are big, some of them are very small. When they are big, means that that particular value is very important to you. So therefore their value, okay, their vectors value will be added into your vector value. Okay, so therefore your original vector and the somebody else's vector somehow will be put together. So it used to be just a house, but now you have broom, and the two together, meaning that you have the meaning of a broom house. So you are adding the information, adding the knowledge together into a refined vector in that vector space. Okay, and this key and query is just to decide how much of their value should be added into you. And this all this the circles here, meaning that how important are the information from each of this to each of this.
Bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast to the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values that can be any real number from -infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from -infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original Transformer paper, there's a really compact way that they write this all down. Here, the variables Q and K represent the full arrays of query and key vectors, respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that V term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many.
Okay, so let's come back to our slide. So, slide here that basically that we have shown this idea of when you have a sentence, each of that has a value, okay, as a vector, and then we will be using some weights, okay, to produce the query, and you will be producing the key, and the key and the query will be, tend together, then they would decide how much of this value, each of this value should be used to update the original value of the it. Okay, and so these are just simply the mathematical notations to describe that each of this xi will produce a query. Each of the xi will produce a key. Each of the xi will produce a vi. And the wq, which is going to be the training we want to do to find out the value of these weights. Okay, there will be one weight matrix for the query, one weight matrix for the key, and one for the v. Now, remember, this W here is going to be independent of the specific question that you're going to ask. It's going to be a universal weight for the language model. Okay, so once you have trained, there will be only one, this weight that's going to be used for every sentence, every single word. Okay, they will be used for every single word for any input. Okay, you will come up with a query, and that query then will be matched with your words, other words in the sentence to produce the key. Okay, so this W here actually is what we call as our large language model. Okay, the large language model actually is going to be used WQ, it's going to use WK, it's going to be used WV. Okay, each of that is going to be one giant, okay, very, very big matrix. Okay, and so the whole learning process for training a large language model is to find all of this. And that all of this are just saying that once you have found them, okay, how do you come up with the answer? It's going to be using this formula. Here again is the picture. Each of the word in the sentence, okay, will be using the W. Here is going to be WV, WK. I'm sorry, this is WK and this is WQ. Okay, so there are actually three big weight metrics here. Okay, and so your specific value will be using the WK to produce your specific K. Okay, and your W value will be used to produce your specific W, uses WQ to produce your specific Q. So everybody actually going to use the same W, WK, WQ, WQV here, but since everybody's original embedding value, okay, your vector in the vector space is different. So when you multiply this one here into that, you're going to produce different query. You're going to produce different key. Your query then will be sent to everybody, and they will match that with their particular key. Okay, so your query, their key, their key will be dot together. Then we'll go through this one here and produce the weight, and that weight then will be added together with your own value. Okay, that will produce you to be your output weight. So your original vector is this, but after sending out the query and they come back with a key, okay, and you multiply with your value, that will be your new vector after the transformation. Okay, so if you compare this again with the computer vision, inside here originally we have some picture. Each of the pixel, okay, will go through this convolution. The convolution will have the output. The output then will be put together, and you have the new set of values in your output, hidden layer output. Okay, so this would go through this multiple times. Okay, in our system, the system here, every single word. Okay, you will go through the encoding. You will go through all this positional thing. Then you go through each of these transformation metrics. And so its value, its original value, okay, from the embedding will be updated through the discussion and the interaction with all other words. Eventually, you will come up with something. Then depending on what you're trying to do the output, okay, like here, it's trying to predict the next word. So when you have the so, you'll produce the next word, it's going to be long, okay? Once you have the so and long, using the two information, then you produce next word to be N. Okay, so everything is going to be after you have produced all these big weight metrics. Okay, you train the system model, then all these transformers actually are just going through each of the values and updating your embedding, and then trying to make the prediction of your next value. Okay. So all of this actually is possible to do at the same time if we have the whole sentence. Okay, because the whole sentence we have the embedding for each single word. Okay, and they all go through the transformation. They all have their position, but the information is going to be cross-referenced. So everybody would have their query. Everybody would generate the key, and then they would know each other. And so therefore, that this is possible to try to do this in parallel. Okay, and that makes the large language model very powerful because that it is able to consider so many things at the same time. Okay, and even though that you have a long sentence. Okay, because each of this can be done in parallel. Okay, everybody would know about all the other tokens, and you will go through all this WQ, WK, WV at the same time. And once you have all of them, then you will be able to take the Q and the K and then do this dot matrix to come up with value. Then this value here can simply go into the value, go into the output, the V here, and this will be multiplied, and you produce your outcome. Okay, so you have some original weights. Okay, you have some original key. You have original your value, and your value your in the embedded space will be updated. Okay. So let me see, what else do I want to watch here? Okay. Let's watch this one here. Let me see what it's trying to say.
Other words they're relevant to. For example, you want the embedding of Fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a Fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, Fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case, something you add to the embedding of creature. So this value vector lives in the same very high dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all of the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for Fluffy and Blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add that I'll label delta E, and then you add that to the original embedding. Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature.
Okay, so that's the whole idea of the transformer. Transformer is for you to be looking the whole sentence, okay? And rather than just read each word, we actually convert each word into a vector, okay? And in the vectors, then we use the big W, which is trend model, okay? And you have the the W for the query, W for the key, W for the V, okay? And then we go through this one here. Eventually, your original embedding, which has no information, okay, except that you are a creature, but adding some other information from the fluffy, from the blue, then will change your embedding into this new thing. Okay, so this is actually a new vector, but this is new vector already. You can see that it captures all the information, not just from creature, but from fluffy, from blue, and then into one. So you can imagine that doing this many, many times, when you have the whole article, okay, and you are trying to understand what's going on, somehow, if you have this embedding here, it's already capturing every keywords from the article. And you can imagine it actually has everything about the whole article. So if you ask a question about the article, hopefully that particular embedding can answer the question. Okay, can already give you the answer from something related to the article. Okay, so the question is that, can you imagine that this particular embedding here actually is able to capture everything or not? And I don't know whether you have noticed or not, but in this let me see, somewhere in here, okay, it's talking about the output.
Numbers. You remember how I said that the value map is factored out?
Okay, so the vector, okay, in the large language model actually has 12,288 dimensions. Okay, so it is trying to capture the knowledge in 12,000 dimensions, more than 12,000 dimensions. Okay, meaning that some dimension is probably capturing the size, some dimension is probably capturing the location, some dimension is probably capturing the color, some dimension is probably talking about history. How exactly each of these dimensions is referring to some semantic information, we don't know, because this is machine learning. Okay, we don't really know what is trying to say each of this weight. Okay, but each of the meaning in each of this vector of 12,288 vector has a value, has 12,828 values, and that's all those specific values is capturing the knowledge about the whole text together. Okay, and so if you ask a question, then it will give you another, the output is going to be a value here. And this value, if we somehow can come up, use that value, then we'll be able to produce the output.
In these two distinct matrices, which I labeled as the value down and the value up matrices. The way that I framed things would suggest that you see this pair of matrices inside each attention head. And you could absolutely implement it this way. That would be a valid design. But the way that you see this written in papers and the way that it's implemented in practice looks a little different. All of these value up matrices for each head appear stapled together in one giant matrix that we call the output matrix, associated with the entire multi-headed attention block. And when you see people refer to the value matrix for a given attention head, they're typically only referring to this first step, the one that I was labeling as the value down projection into the smaller space. For the curious among you, I've left an on-screen note about it. It's one of those details that runs the risk of distracting from the main conceptual points, but I do want to call it out just so that you know if you read about this in other sources. Setting aside all the technical nuances, in the preview from the last chapter, we saw how data flowing through a transformer doesn't just flow through a single attention block. For one thing, it also goes through these other operations called multi-layer perceptrons. We'll talk more about those in the next chapter. And then it repeatedly goes through many, many copies of both of these operations. What this means is that after a given word imbibes some of its context, there are many more chances for this more nuanced embedding to be influenced by its more nuanced surroundings. The further down the network you go, with each embedding taking in more and more meaning from all the other embeddings, which themselves are getting more and more nuanced, The hope is that there's the capacity to encode higher level and more abstract ideas about a given input beyond just descriptors and grammatical structure. Things like sentiment and tone, and whether it's a poem, and what underlying scientific truths are relevant to the piece, and things like that. Turning back one more time to our scorekeeping, GPT-3 includes 96 distinct layers, so the total number of key, query, and value parameters is multiplied by another 96, which brings the total sum to just under 58 billion distinct parameters devoted to all of the attention heads.
Okay, so what it says that in the GPT-3, okay, the total number of such layers actually is 96 layers. So you do this 96 times, okay? And in each of the 96 layers, okay, you have so many queries and you have so many heads and you have so many embedded metrics, okay? Each of this is a vector, okay? And you have so many 128, okay? Head means that just like in our computer vision, we actually have multiple filters or multiple channels, okay? So each of this head is trying to capture one channel. In the computer vision with the RGB, at least we have 3 channels, okay? But after we have gone through the convolution, it becomes to be more channels, and each of the channel actually have some specific in it. The hash here also is trying to capture different semantic things, okay, in the language. So in any case, in GPT-3 is a total of 96 layers, and it has 96 different heads, different type of things going through this. Each of them, is trying to do the vector of this, and inside each of the query and value and embedded vector, okay, is 128. Okay, so the total size together, okay, the total number of weights that is, trying to build in the GPT-3, if we add it together, it's going to be 97 billion. Okay, but actually that the total size is organized into 27,000 metric.
A billion that are in the network in total. So even though attention gets all of the attention, the majority of parameters come from the blocks sitting in between these steps. In the next chapter, you and I will talk more about those other blocks and also a lot more about the training process. A big part of the story for the success of the attention mechanism is not so much any specific kind of behavior that it enables, but the fact that it's extremely parallelizable, meaning that you can run a huge number of computations in a short time using GPUs. Given that one of the big lessons about deep learning in the last decade or two has been that scale alone seems to give huge qualitative improvements in model performance, there's a huge advantage to parallelizable architectures that let you do this. If you want to...
Okay, so let's come to look at our things. Okay, so in the slide, it's talking about, we have originally we were using token, but we also have the positional embedding, because the embedding is, the position is important. The words in front of you, the words after you. Okay, so therefore, whenever it is trying to do this transformation, actually it encodes the position into your embedding. So your vector actually not just about the meaning, but also about position of each of the vector. Okay, so in any case, it is going through some of this token and the position. Okay, and it's just trying to add the position, number 1, number 2, number 3, number 4, number 5, and each of the word, okay, you will have the word embedding together, okay, before you send it to the transformer to try to process the attention, okay. Scale. I think we all know by now from all different generations of the GPT, ChatGPT, Llama, and other things, the size actually somehow is quite critical to the success of the large language model. Okay, and this is people call as a scaling law. Okay, large language performance depends on first the size of the model. the number of parameters, okay, that is inside of this matrix, and inside of each of its different paths, inside of different layers, okay? So the model size somehow, okay, is making the performance, the output quality to be not linear, but somehow it's almost like exponential, okay? Secondly, the amount of training data we use with the same model size, but the more information you use for the training, okay, the more successful your model will be. Okay, so the data size is another size. Model size is something that whenever you run, you need so many parameters. Data size is before you run, when you're doing the training, how much information the system has learned from, okay, is the data size. Okay. Thirdly, it's going to be the computational size, okay, which is the in terms of flop, in terms of the GPU and such, okay. So all three together actually is something people have studied, and they have found that the scaling law. Scaling law means that the loss, okay, somehow is very related to is a function of the parameter, the data size, as well as the computing budget. Okay, so the loss is going to be using this formula here. Okay, it's just kind of in general that there's some way for us to say that the bigger the n, the bigger the d, the bigger the c. Okay, the less loss we're going to see. Okay, and this alpha n and alpha d and alpha c, this is something that just in terms of the concept, it's just a general thing. Okay, it's not specific. Okay, so so GPT-3, we have just said that with 96 layers, okay, with a dimension of 288, would have 175 billion parameters, and if you think about so many parameters, when you try to run a large language model, every sentence you give to the language model, you need to go through each of these layers. You need to go through each of these dimensions, okay? So each of these parameters needs to be used in order for you to produce the output. And that's why that computing power actually now is very important, because any simple question you ask, we're using this large model, and that large model has 175 billion parameters. Any simple question you ask. Okay, so that's why that now, even though we are using ChatGPT, we are using something, okay, but you are actually being converted your token, and your token still is going to be sent to some machine that will be holding this large number of parameters. Let's just have a simple question. Okay, 170 billion parameters. If each parameter is a byte, 175 billion means how much data memory size you need to have. In order for us to have each of these parameters, if each parameter is 1 byte, to have all this, how big the memory do you need? Megabyte, gigabyte, terabyte, or picobyte, petabyte. Basically, the median is a megabyte. The billion is what? A gigabyte. Okay, so 175, basically we're talking about gigabyte if each parameter is a byte. 170 gigabyte, is it big or not? For our personal computer, for your laptop, it's big. For server, maybe. Okay, but of course that still is reasonably big. okay, because for server to have gigabyte memory, okay, if some server, of course, they can have, 20 gigabyte, 40 gigabyte, 48, 96, okay, but if 170 gigabyte is not impossible, okay, but still, of course, that we want to be able to, that you only to say that when you want to run, okay, or when you're trying to say you want to do the training, okay, we can try to compute all of this in parallel. Okay, when we are going to do the training, you give the whole sentence into the system. Okay, the system will be able to cross-reference each other. But at the inference, when you actually ask the question, your answer will be generated one word or one token at a time. Okay, so therefore, every time when you do that, you need to run this. Okay, so you don't need to recompute those values, but you need to get the output over and over and over and over again. Okay, and so therefore, this is going to be something that actually is quite intensive. Okay, and so quite often that we are trying to come up with some way for us to be able to have a simpler model. Okay, or we're trying to cut down the number of parameters. Okay, that we can reduce. Okay, we don't want to have always to have some gigabytes of parameters. We don't want to always have to be holding so much memory inside of our large language model, okay? And so there are some technologies that are trying to make the large language model to be more parameter efficient, okay? We try to reduce the enormous number of parameters. We're trying to reduce the size of the gradient descent. Okay, we're trying to reduce the processing power. We try to reduce the memory, and we try to reduce the amount of time that it would take for us to try to produce the model. Okay, and in general, all of this is that we're going to try to do after we have built a large language model. Can we somehow fine-tune it to make it to be more parameter efficient, meaning that we don't need to have all of those 175 billion parameters, okay? And there are some different strategies, okay, to do that, okay? So we can efficiently select a subset of those parameters, okay, when we're doing the fine-tuning, okay, or we can only update, some of the parameters, okay? One way to try to reduce the size is to not to keep the whole thing, WQ, WK, WW, WV, okay, or the whole matrix. Rather, somehow we can divide them or we can convert them into some smaller matrix, okay? And I'm not going to go into detail, but basically what we're trying to do is that suppose you have original weight, which has been produced by the large language model. If we can find two metrics, which is one is this D times R, the other one is R times K, and the A times B, okay, is similar to W, then we can reduce the size, which is original D times K into D times R plus R times K, okay? So by simply looking at this picture here, you can see that the amount of space we need to hold these parameters, okay, will be smaller than the original big matrix, okay? So this is one way to try to reduce size, which is called LoRa, is to convert any original weight matrix into two smaller matrices. If these two smaller matrices, they multiply together, the value is similar to this, okay, then we don't need to keep this, but we only need to keep A and B, okay? And this is a very effective way to cut down the total memory size we need to store. So for example, suppose they say you have 1,000 by 1,000, okay? So this is going to be 1 million. 1,000 by 1,000 is going to be 1 million. But here, if you can change it to be 1,000 by 10, okay, then this is going to be 2,000. 1,000 by 10, this is going to be 10,000, and this is going to be another 10,000. So it's going to be total 20,000. So instead of 1 million, you have 20,000. You're cutting down the space to be, only originally 2% of the original space. So instead of 170, it can, be becoming to be only about 3 billion. Okay, and that would make your system to be much smaller. Okay, even though in terms of the computation, okay, you still need to, multiply all of this together, but in terms of the space for you to be holding the parameter is going to be much simpler. Okay, let's take a break. We'll come back and talk about some more about the large language model. But before I continue, I would like to look at this video again. The video we have just seen is chapter 6, and this is chapter 7. And chapter 7 is trying to talk a little bit more about the large language model. But let's try to watch this together to see that whether you can, understand what it's trying to say in this very short video earlier here, the refresher.
In a piece of text and predict what comes next. That input text is first broken into a bunch of tokens, which means little chunks that are typically words or little pieces of words. And each token is associated with a high dimensional vector, a long list of numbers. This sequence of vectors then repeatedly passes through two kinds of operation. Attention, which allows the vectors to pass information between one another, and then the multi-layer perceptrons, the thing that we're going to dig into today. And also there's a certain normalization step in between. After this sequence of vectors has flowed through many, many different iterations of both of these blocks, by the end, the hope is that each vector has soaked up enough information, both from the context, all of the other words in the input, and also from the general knowledge that was baked into the model weights through training, that it can be used to make a prediction of what token comes next.
Okay. So the key words here is that when you give an input, originally input sentence, the input sentence will be converted into the embedding, each of them would have some vectors. And all of these vectors will go through attention to try to find out more information about each other. Then you will go through also the language model. The language model actually already has been trained, and it has some knowledge, not from your sentence only, but from where? From all articles he has read before when we try to train the model. So actually it has two sources of information. One is the specific question that you are asking now, and the other one is what we call as a pre-trained model. So the pre-trained model is being trained using gigabytes and gigabytes of information is collected from around the world, from the web, from whatever database that is supposed to train on, okay? So that information is already captured somehow in those metrics inside of the large language model. So using that and also your sentence, you will be able to produce the embedding, and you will be, after you, at the end of your sentence, you will produce one specific vector, and that particular vector will try to help you to make the prediction, for example, the next word, okay, or the output to say that yes or no, or maybe that you will try to, decide that whether this is a good comment or this is a bad comment. So this particular answer here is the vector that we think it captured all information from both your sentence or your input and also the large language model itself. Okay.
The key ideas that I want you to have in your mind is that all of these vectors live in a very, very high dimensional space. And when you think about that space, different directions can encode different kinds of meaning. So a very classic example that I like to refer back to is how if you look at the embedding of woman and subtract the embedding of man, and you take that little step and you add it to another masculine noun, something like uncle, you land somewhere very, very close to the corresponding feminine noun. In this sense, this particular direction encodes gender information. The idea is that many other distinct directions in this super high dimensional space could correspond to other features that the model might want to represent. In a transformer, these vectors don't merely encode the meaning of a single word, though. As they flow through the network, they imbibe a much richer meaning based on all the context around them, and also based on the model's knowledge. Ultimately, each one needs to encode something far, far beyond the meaning of a single word, since it needs to be sufficient to predict what will come next. We've already seen how attention blocks let you incorporate context, but a majority of the model parameters actually live inside the MLP blocks. And one thought for what they might be doing is that they offer extra capacity to store facts. Like I said, the lesson here is going to center on the concrete toy example of how exactly it could store the fact that Michael Jordan plays basketball. Now this toy example.
Okay, so this is talking about MLP, okay? Inside of this large language model, actually, we have not just all those metrics, but also we have MLP. MLP is just like in the computer vision machine model. At the end, we have the fully connected layer. Okay, inside of this large language model, it has many such fully connected layers as well. Those fully connected layers have many different weights. Each of them has a lot of weights. Okay, so the total number of weights in the fully connected layer actually is bigger than the total number of parameters in those matrices together. Okay, and in this discussion here is trying to give an example. Okay, those fully connected layer or MLP is able to do, okay, in a simple example that it's going to talk about now.
First, we'll suppose that one of the directions represents the idea of a first name Michael, and then another nearly perpendicular direction represents the idea of the last name Jordan, and then yet a third direction will represent the idea of basketball. So specifically what I mean by this is if you look in the network and you pluck out one of the vectors being processed, if its dot product with this first name Michael direction is 1, that's what it would mean for the vector to be encoding the idea of a person with that first name. Otherwise, that dot product would be 0 or negative, meaning the vector doesn't really align with that direction. And for simplicity, let's completely ignore the very reasonable question of what it might mean if that dot product was bigger than 1. Similarly, its dot product with these other directions would tell you whether it represents the last name Jordan or basketball. So let's say a vector is meant to represent the full name, Michael Jordan. Then its dot product with both of these directions would have to be 1. Since the text, Michael Jordan, spans 2 different tokens, this would also mean we have to assume that an earlier attention block has successfully passed information to the second of these 2 vectors, so as to ensure that it can encode both names. With all of those as the assumptions, let's now dive into the meat of the lesson. What happens inside a multi-layer perceptron? You might think of this sequence of vectors flowing into the block. And remember, each vector was originally associated with one of the tokens from the input text. What's going to happen is that each individual vector from that sequence goes through a short series of operations. We'll unpack them in just a moment. And at the end, we'll get another vector with the same dimension. That other vector is going to get added to the original one that flowed in, and that sum is the result flowing out. This sequence of operations is something you apply to every vector in the sequence, associated with every token in the input, and it all happens in parallel. In particular, the vectors don't talk to each other in this step. They're all kind of doing their own thing. And for you and me, that actually makes it a lot simpler, because it means if we understand what happens to just one of the vectors through this block, we effectively understand what happens to all of them. When I say this block is going to encode the fact that Michael Jordan plays basketball, what I mean is that if a vector flows in that encodes first name Michael and last name Jordan, then this sequence of computations will produce something that includes that direction basketball, which is what we'll add on to the vector in that position. The first step of this process looks like multiplying that vector by a very big matrix. No surprises there, this is deep learning. And this matrix, like all of the other ones we've seen, is filled with model parameters that are learned from data, which you might think of as a bunch of knobs and dials that get tweaked and tuned to determine what the model behavior is. Now, one nice way to think about matrix multiplication is to imagine each row of that matrix as being its own vector and taking a bunch of dot products between those rows and the vector being processed, which I'll label as E for embedding. For example, suppose that very first row happened to equal this first name Michael direction that we're presuming exists. That would mean that the first component in this output, this dot product right here, would be 1 if that vector encodes the first name Michael, and 0 or negative otherwise. Even more fun, take a moment to think about what it would mean if that first row was this first name Michael plus last name Jordan direction. And for simplicity, let me go ahead and write that down as M plus J. Then taking a dot product with this embedding E, things distribute really nicely, so it looks like M dot E plus J dot E. And notice how that means the ultimate value would be 2 if the vector encodes the full name, Michael Jordan, and otherwise it would be 1 or something smaller than 1. And that's just one row in this matrix. You might think of all of the other rows as in parallel asking some other kinds of questions, probing at some other sorts of features of the vector being processed. Very often this step also involves adding another vector to the output, which is full of model parameters learned from data. This other vector is known as the bias. For our example, I want you to imagine that the value of this bias in that very first component is -1. Meaning our final output looks like that relevant dot product, but -1. You might very reasonably ask why I would want you to assume that the model has learned this, and in a moment you'll see why it's very clean and nice if we have a value here which is positive if and only if our vector encodes the full name Michael Jordan, and otherwise it's 0 or negative.
Okay, I think this captures the most important concept in the MLP. So inside of the transformer, okay, inside of the large language model, we have the transformer, which will be updating the vectors, okay, from its original form into some form that capture the contextual or the meanings from all the surrounding words. After you have captured that, then it has something, okay, and that something now we're trying to use the knowledge from the previous articles, not about the sentence, but from other previous, maybe journal, maybe newspaper, maybe some reports, okay? Somehow it needs to know, okay, it needs to remember there's a person called Michael Jordan, okay? And it's able to capture that in the big matrix here. And so therefore, if you have a text, somehow that refer to Michael and Jordan and something, okay, then you will be able to match some previous knowledge that Michael Jordan actually is a basketball player. Okay, and then you produce the output, which is going to be positive. Okay, and also you will be able to produce something, okay, which actually capture the knowledge, not just from your sentence, but from some earlier article, from earlier library, from earlier newspaper, okay, and give this some weight, and then change this vector space to that knowledge in the hyperspace, in the vector space, that's referring to say, well, it's not just somebody named Michael, it's not just somebody named Jordan, but this is about a specific person. And that person is Michael Jordan. That person used to play basketball. That person, was in this, I don't remember which team he used to play for. I remember was in Chicago. What's the name of the team? Huh? Well, yeah, could be. Okay, so the matrix here needs to remember those information. And so that when you have the Michael Jordan and you multiply into this, and then some vector values, okay, some specific value in the vector space will say, yes, this is the person who's referring to in that particular position, in that particular area, and about certain facts. And with that, then you will be able to, whenever it sees Michael Jordan, you can answer questions captured in that particular space. They used to won the championship multiple times. The height of the person, the background of the person, and such. All of that are already in here. Okay, so large language model is actually very complicated. It's taking a text, convert it into embedding, and so we now are able to store the information somehow in this vector space, and the vector space actually, has 12,000 to 88 dimensions. Okay, and that space somehow have all of the knowledge captured in all of these metrics here. So when you go through the large language model by using a sentence, then you will be able to match with all of the previous facts, previous articles, okay? And you can produce something in here that capture those knowledge. When you capture that knowledge, and if you have some specific question or specific something you want to ask, then you can use that knowledge, and then you will be able to output and to tell you, say yes or no, to tell you, say something about that particular person. Okay, so MLP is the part, okay, that actually both in computer vision. In computer vision, that we have all of these convolutional layers that is able to capture all the features. At the end, we strengthen, we line up all the features into one dimension. Then we run through the fully conditioned layer, okay, and then we're able to produce the output, whether it's classification, whether it's object identification, and such. MLP in here is also the place similarly when you have all of those embedding, okay, already been used attention, then they will be able to give you the result, which is going to be your final fact, okay, your final answer, okay. So so large language model actually is quite complicated. I'm not going to play the rest of the video, but the rest of the video basically is talking about the structure of this MLP. Okay, it's talking about how do we actually, what is the size of the parameter, okay, and then how the informations are put together in a superposition, okay. But anyway, at the end here is that we actually So
Also, from the general knowledge that was baked into the model weights through training, that it can be used to make a prediction of what token comes next. One of the key ideas that I want you to digging into the details behind transformers, attention. It boils down essentially to a pair of matrix multiplications with a simple something in between. However, broken into a bunch of tokens, which means little chunks that are typically words or little pieces of words. And each token is associated with a high dimensional vector, which is to say a long list of numbers. This sequence of vectors then repeatedly passes through two kinds of operation. Attention, which allows the vectors to pass information between one another, and then the multi-layer perceptrons, the thing that we're going to dig into today.
okay, so each layer, okay, already have the attention, already have the multi-layer MLP, okay? So, but in computer vision, how many MLP do we have? In most of the computer vision architecture we have seen, in the front, at the lower layer, what do we have? Convolution. At the end, we have the fully connected layer. In the large language model, you can imagine the attention here is similar to the convolution. Convolution is trying to find out some information about each individual, kind of metrics, right? Because we have this 3 by 3 or 5 by 5 convolution. So attention is like that too. In a sentence, we're trying to find anything about our neighbors. Okay, and after we have that, then we go through the multi-MLP, which is similar to the computer vision. We have the fully connected layer. But then you repeat this.
And both normalization step in between.
Right.
After the sequence of vectors has flowed through many, many different iterations of both of these blocks.
Right. So in each of the blocks, actually, there's already a multi-perceptron layer. Okay, so there's an MLP. So what does it mean to be fine-tuning a large language model? Are you going to go into each of this and say, oh, I'm going to change the MLP here, I'm going to change MLP here, I'm going to change MLP here? Are you? No. Okay, because that's too complicated. Okay, so even though we have used the same word, fine-tuning in computer vision, in NLP, they are different things. The skills actually is quite different. Okay, in the fine-tuning here, if you read this slide carefully, what do you see? This one here says this is self-supervised training. Okay, but what does it say here? Supervised training. Okay, so when you are doing the NLP, when you're trying to do the large language model, originally you just collect a lot of information and you store it in the system and say, okay, now read it. Okay, try to find out information yourself. But after the model is trained, then you try to say, okay, now I'm going to give you some specific question and answer. Okay, if I give you a question like this, I want you to come up with an answer like this. That's a supervised. Okay, you run it, and then you tell the system, wrong answer. Do it again. Then the system is supposed to take it as a loss function and go update all this model by itself. It's going to go update this by yourself. We are not going to try to say, oh, you're going to update here and here. The system will do it because we are going to try to do retraining. Fine-tuning here is not so much of just change part of the model. It's actually changing, again, the whole thing. But why is it fine and this is pre? What's the difference? The fine-tuning means that it should be smaller, right? In the computer vision means changing a smaller number of parameters, only in the NLP, only on some layer, not the rest of the layers. But in here, fine-tuning means that we're not going to be using large data set. We're going to be using specific data set. So specific data set and large data set, what's the difference? This is going to be hundreds of gigabytes, thousands of gigabytes, terabytes. But the specific target domain here is going to be much smaller. Okay. So the fine tuning here, and that's something that we have talked about last time, is kind of very similar in the sense that we could have the fine tuning, we can have instructional fine tuning, or last week, what was the topic? What was the topic for last week? Do you remember? What did we talk about last week? Reg. This was one of the slides in the last week, right? Okay, let's look at this picture again. Do you see pre-training? This is pre-trained, original large language model. Where is fine-tuning? Domain knowledge, fine-tuning. Where is red? Domain knowledge, red. So what is the difference between this and this? The picture is just a simple picture, and this picture, in a way, is not totally correct, because this is a large language model, right? This large language model, originally we use some large data set, okay, which we collected from the whole world, okay, collected from the web, and this is going to be hundreds of gigabytes. The target data set here is your knowledge base. In the homework, how big is your knowledge base? How big? How many files are you supposed to read? How many files in the homework? PDF file. How many? Have you started doing your homework yet? 6? Something like that. 10 files. 10 files, 10 PDF files, compared with a large data set. This is more than 100 gigabytes. That's what we're talking about. The difference between this and this is that originally we are using very, very huge data to train the model. Okay, but after we train the model, we don't go in ourselves to say, I want to change you. But we say, okay, I'm going to give you some extra data set. This extra data set, if I use my first pre-training, okay, fine-tuning, that I'm going to tell you, say, okay, I have some question I'm going to ask you, okay, and I want to check your answer. If your answer is correct, then I'll say yes. If your answer is incorrect, go back. Somehow you change yourself, the large language model, okay? So the large language model will be taking this fine-tuning. You can think of that almost similar to our test data set in the computer vision. But in your test data set, when you run the data set, do you go back to do the training? Well, you don't do it in a test data set, but you use the validation data set. When you have a validation data set, it's not good. Then what do? You go back and change the parameters, right? When you do the training, do you use state propagation in the computer vision? Yes, right? When you use the validation data set, do you do state propagation? No, you don't. So why do you want to do the validation data set? You want to see the loss curve. You only see the loss curve. You see that with the loss curve in the validated set compared with the training data set curve, whether they are actually following the same trend or not. And then that make you decide whether you should continue to do the training or not. Right? And in here, okay, similarly, you have something which you say domain data set. I'm going to use that to check you.
to test whether you are good or not. And if you're not good, I'm going to tell you no wrong answer, but I'm not going to tell you how you should change it. How you should change your model. We just simply tell you, say it's not good enough. Okay, so this is the fine tuning. Okay, the fine tuning here is going to be almost like self-training, but it's supervised self-training. Okay, now the third one, red. So what is the difference between this and this? In the fine tuning, actually, we tell the system model to say, your answer is not good. Go back and change yourself. Change your parameters in the NLP, change your parameter in the matrix, whatever. Okay, but you need to modify the model. But when we do in the red, you have the domain knowledge. You create what? Inside, you create what? The first step for you to try to use the domain data set is do what? Use the domain, yeah, okay. You use the domain data set here, okay, is for you to try to create this is what called this. What is this? What is the vector database? Vector database is from your original data, okay, that is going to be in your specific domain. And you do the chunking, okay? And the chunking here is to cut it into smaller pieces. Then you use the embedding, then you use this vector database. So the vector database, okay, is going to be something every time when you ask a question, you will go to vector database and tell me whatever information from here is relevant to my query, so that you come up with this extra information. What? For you to combine with your query, so that your query and this information will be used to ask the large language model. Okay, and hopefully you will produce a good answer. The inside of a large language model, when you use the RAG, do you change the model or not? You don't. Okay, because this is a model which you are going to be called OpenAI to ask the question. This is the model that you're going to be asking, from the Gemini. Okay, this is something is going to be from the cloud. You're going to be asking the question. Ask the LLM to give you the answer. But in RAG, the only thing that you are going to do is to say, I'm going to ask you a question. And by the way, I have some extra information for you. I provide you with extra information so that you can answer my question. Okay, but that is not fine-tuning. Fine-tuning is to say, okay, I have some information, okay, that I already know the answer, okay, and so let me see. Okay, so here, for example, you have some feedback, okay, so you have a large language model. You have super fine-tuning means that you ask the question, and the large language model actually give you an answer, okay? And then you say, oh, this is actually correct or not, okay, or this is something good or not. You tell the system to say, please change yourself. So the next time, if I ask the same question, you will give me a better answer. And this decision making to say that whether your question is good or not, you optimize, could be something from the human. Human will say, oh, your answer is good. This is very good. And so all this optimized in the fine-tuning in a large language model is actually changing the model, actually change the model. So LLM need to go through the training, not just by reading the information from outside, but also try to give you the answer, and somehow the answer will be used to tell the system to say, no good, no good. Don't answer in that way. Next time, if I ask you the same question, give me some other answer. Okay, so the fine tuning in the large language model actually will, okay, update the model. But when we try to do RAG is for you to be producing something which is going to be outside the large language model. You produce this vector database from the data you provided using your own embedding operation. And you produce this vector database, and that's going to be your own knowledge. And this knowledge is not going to be given to LLM. So the LLM will not have your private information. That's why companies want to use the RAG, because they have their private information. They will be collected in their company's vector database, and that's going to be local. When you ask a question, it's not going to give the whole database to the LLM, but you'll be looking at this and then try to get some information which is relevant, but not the whole knowledge. Okay, and then you will say, oh, I'm going to ask you a question, and by the way, I have some extra information that you can use to be voluntary, but you use the same LLM. So LLM, after you have asked it multiple times, LLM is still the same original LLM. It doesn't change. Okay, so RAG is not fine-tuned. RAG does not change LLM. So whenever we talk about fine-tuning, okay, it's actually the model is going to be changed. Okay, so in the original, when we look at this particular figure again, okay, we have the pre-training, we have the fine-tuning, we have the instruction fine-tuning, which is make the result to be more human-like. All of this actually is for those companies, OpenAI, for Google, for Meta, for them to be doing to produce their own models. They will be updating their models. But RAG does not do that. RAG is for you to be producing something outside you keep in your company, you keep in your organization, you keep in your own personal database, but the large language model is going to be outside. So the large language model is actually able to capture the knowledge from its earlier training, but not from your own private data set. Okay, so if I want to make a different RAG, do I need to change the LLM? No, because if you want to make different RAG, you just give it different raw data. From company A, I give my own vector database. Company B, I have my own raw data, I have my own vector space. I'll ask the same question. For company A, you should get an answer for company A. You ask the same question for company B, you should answer the question for company B. They should have different answers. Original LLM cannot do that because it doesn't know whether company A, company B, whether you are big company or small company, but you can tell them the information here, say, oh, here, by the way, my company has 10,000 employees. And here says, oh, my company has 100 employees. When you have 100 employees, when the 10,000 employees, of course, your large language model should be smart enough to give it different answers. Okay, so that's the idea of the RAG. Okay, so RAG, from the large language model's point of view, is nothing to do with the model. Okay, but it is something we are trying to do to make it to be something more useful to us. Okay, and last time that Professor Zhou has shown this picture, so let's look at this picture again. Okay, let's try to see that whether it makes sense or not. Okay, so it compares fine-tuning with RAG, and you have the prompt engineering. Okay, next time we'll spend a little bit of time to talk about prompt engineering as well as other tools, and of course that we'll try to conclude the whole semester. Okay, but fine-tuning, it says this is LLM response optimization. Want the model to respond in a specific way. But here it says a content optimization, okay, is able to try to make the content to be more correct. So what is this? What is this? And what is this? Okay, let's look at prompt engineering in RAG. What is the difference between them? What do you understand about prompt engineering? Prompt engineering is what you ask the question in a specific side, right? In a way so that we can make the LLM to give us more specific answer, right? But RAG actually is one form of prompt engineering, right? Because it's you outside of the LLM. LLM is there. I'm asking the question and I'm asking simple question. I'm asking more specific question. Or in addition to the question, I also give you some extra knowledge and give it to the LLM. So this one here is going to make your content to be more optimized because I have extra knowledge for you. Prompt engineering is just trying to ask you in different way so that you can answer in the way I like. But I don't have extra information for you. But RAG, because I have extra information for you, so now your answer should be more correct to my application. But what about this? This actually is, in a way, fine-tuning is not prompt engineering. Fine-tuning is to say, yes, I ask you a question and you give me answer and I correct you to say yes or no. But it's supposed to be that you trying to change the response, but by changing your knowledge. I have some specific data, and you should use those specific data, domain data, and test to see that whether your knowledge is correct. If your knowledge is correct, change yourself. Okay, so you are actually changing the language model. You are not just to say, I'm going to give you some extra question for you to answer, or give you some extra information for you to answer. But this is actually changing so to do the fine tuning, usually what you need to have some extra information. Also, you need to have a language model that is open. The language model allow you to update the parameters, allow you to update the weights. But you know that most of the large language model right now, they don't allow you to update. Okay, that's why that in last week's slide, if you go look at, Professor Zhou said that you can use the Ollama, right? In Ollama, it's an open system, so therefore you can download it and you can try to do the Ollama open system or not. Gemini is a open. Llama is an open system, right? I think Llama is an open system. Yeah, Gemini is not open because Gemini by Google is not an open system. You cannot change it. But Llama you can change it. So Ollama actually then you can try to do both the fine tuning as well as the RAG. Okay, but these are two different approaches. One is actually changing the model, updating the parameter inside the model. The other one is not changing the model, but I give you extra information. Okay, so if I ask you a question about RAG, the difference between RAG and fine tuning in the final exam, what should be your answer? Don't tell me which one is easier or which one is more difficult. What's the difference? The most important difference. This is changing the model. This is not changing the model. Okay, RAG doesn't change the model. Prompt engineering doesn't change the model. You're still using the same model. ChatGPT-3, ChatGPT-4, still using the same LLM. But this one here is to say, if you have an open model, then I can try to change it. Okay, in computer vision, do you change the model or not? If you do fine tuning? Yes. Okay, you update a few layers. Okay, you don't update the whole layers, you do the upper layers. Okay, and that is the meaning of the fine tuning. So kind of both are the same. You are changing the model, but the way that in the large language model, LLM fine tuning, you don't know what you're changing. You just tell the system you're doing good or you're doing bad. And the system training is supposed to change by itself. In our computer vision, we say, oh, take away this layer, create a new upper parameters in those layers for me. Those are the fine tunings. Okay. Okay. So that's all I want to talk about today. And next week will be our last lecture. Okay. I'll talk about some more things, and I'll also review the whole thing that we have talked about this semester to prepare you for the final exam. Okay, I'll see you next week. Thank you.